Hi, everyone. Today, we are very happy to have Nicole Halpern give us our high energy theory seminar on the linear growth of quantum complexity. Thank you so much, Nicole, for accepting to be here and looking forward to your talk. Please.
Thanks very much for the invitation. It's good to be here, even if virtually. This is a talk about quantum complexity, which is kind of a vague term. There are many different types of things that are called complexity. For instance, the Kolmogorov of complexity of something is the size of the smallest program needed to output that thing. Computational complexity, many of us, probably not only me, learned about in actually quantum computing class. Network complexity characterizes brains and social networks. I actually have done some work on that, but I'm not going to talk about it here. And there are other uses of the term complexity, but the type of complexity that I'm going to talk about is kind of generically named quantum complexity. And it's been advocated for by a number of people. I'm going to focus on the perspective brought by Adam Brown and Lenny Susskind. By quantum complexity, I mean the difficulty of implementing a unitary on some set of n subsystems, such as qubits. For instance, in the absence of noise, to implement a unitary that's just the identity operation, you don't have to do anything. So the complexity is 0. And according to a counting argument, the maximum possible complexity scales exponentially with the system size. There are many different ways to quantify complexity. One was developed by Michael Nielsen and friends. Michael and friends imagined that we have our quantum many-body system, that it's evolving under some fixed Hamiltonian in time. At first, the unitary that is implemented is just the identity operator because the Hamiltonian hasn't had any time to act. But as time progresses, the evolution experienced by the system traces out some trajectory in the space of all possible unitaries. We can introduce a metric to this space and use differential geometry to calculate the distance from the identity, which we think of as the sort of origin, and the finally implemented unitary. Because of that differential geometry, this method is beloved in high energy theory. There's a related method for quantifying complexity that's beloved in quantum information. I'll call this the exact quantum circuit complexity. Let U denote an n-qubit unitary. Let's define C of U as the smallest number of 2-qubit gates that we need to implement that unitary. These gates don't have to be geometrically local. The exact quantum circuit complexity has been shown to upper bound Nielsen's complexity. We can understand intuitively why through this picture. Here is the origin in the space of unitaries, and here's the unitary that we want to get to. This smooth red path represents the trajectory traced out in Nielsen's picture, and this jagged green line represents the path traced out by a circuit. There are jags here because the circuit involves the application of discrete gates. Since this green path does consist of these jags, it isn't smooth, so it isn't as short as it could be. It isn't as short as the red line. However, in an approximation scheme that I'll discuss later, the opposite relationship holds between these two quantities. Quantum complexity has emerged recently as a very useful concept that's been unifying a number of spheres of quantum many-body physics. Most importantly to this community, high energy theory. You would know this story better than I do, probably most of you. The use of quantum complexity in high energy theory involves, to a large extent, the wormhole growth paradox in ADS-CFT. In ADS-CFT, we have some space-time and we have some conformal field theory that participates in a duality. In the ADS space-time, we can have two black holes connected by a wormhole, and the wormhole's length or volume can grow linearly in time for an exponentially long time. And we can ask, what is the dual of this wormhole volume in the CFT? The CFT is in some quantum state psi that has a number of interesting quantities that we can measure. local observables, and even out-of-time ordered correlation functions. But these quantities reach their equilibrium values much more quickly than this wormhole volume does. The wormhole growth paradox is, how is it that there is supposedly a duality between these two pictures, but this picture has a quantity that grows in this particular way over a very long time, and the CFT seems not to have a corresponding quantity that grows with the same time scale. A resolution was proposed in the complexity equals volume conjecture. According to it, this wormhole volume is dual to the quantum complexity of this quantum state. Since this resolution was proposed, other alternatives have been proposed. Complexity could equal some action in the space-time, or I recently saw a paper that said was entitled complexity equals anything. But anyway, the quantum complexity is a useful concept to think about in this high energy theory picture. It's also useful to think about in quantum computation in the context of trying to achieve an advantage or quantum supremacy with a quantum computer. We can achieve an advantage with a quantum computer upon preparing a state that's complex enough that it's very difficult to simulate classically. In Kinet's matter, we might have a Hamiltonian that has a gap and it's in a non-trivial topological phase, just if the ground state has a sufficiently large complexity. So a complexity that grows more quickly than a constant in the system size. So quantum complexity has been a useful concept across many body physics recently. This background, and in particular the high energy theory portion of it, motivated Adam Brown and Lenny Susskind to write this paper, which contains some prominent conjectures about complexity. The first conjecture is an answer to the question, Mary, Mary, quite contrary, how does your complexity grow? The conjecture is that under some typical random dynamics, the quantum complexity is expected to grow linearly in time for a time that is exponentially large in the system size. Second, they posited that one can define a resource theory for uncomplexity. This line contains a few pieces of jargon, so let's break them down. What do I mean by uncomplexity? Well, let's shift from thinking about just the complexity of unitaries to the complexity of quantum states. Let's say that a state's complexity is the difficulty, something sort of like the number of gates needed to prepare that state from a simple tensor product. The uncomplexity is the maximum possible complexity minus the actual complexity, a gap. This gap is useful. For instance, when we want to use a quantum computer, then we feed it one of these simple tensor products. So closeness to the simple tensor product is useful. The computer uses this simple tensor product as scrap paper on which it writes its calculations. Since uncomplexity is useful, we could say it's a resource. And in quantum information theory, there's a construct called a resource theory. This is a simple information theoretic model for any situation in which constraints restrict the operations we can perform and the systems we can access. The resource theory framework is actually one of my home bases where I've grown up scientifically in part. We use resource theories to formalize operational tasks like the distillation of high quality entanglement from low quality entanglement, and to calculate the optimal efficiencies with which we can perform those tasks. So conjecture number 2 is that one can define a resource theory for uncomplexity. Over the past few years, I've had the pleasure and privilege of working with a wonderful team of people to prove these conjectures. Jonas Haferkamp, Philipp Feist, and Teja Kothakunda are in Jens Eisert's group in Berlin, and Anthony is in my group in Maryland. Actually, Jonas is presenting about this first paper at QIP this week, so maybe you have or will be seeing a taste of this work, but this seminar should provide more detail. This paper contains the proof of the first conjecture, and this paper contains the proof of the second conjecture, the construction of the resource theory. I'm going to focus in this talk on paper number 1, and then in a couple of weeks, I believe, Anthony is going to talk about our resource theory. Here's where I'd like to go in the rest of this talk. First, I'd like to describe why the problem requires a paper, why this has become a prominent conjecture. Then I'll describe the setup and introduce a set of terms and with them a way of thinking about the problem. And I'll present the main theorem about the linear growth of complexity and sketch the proof. Finally, I'll talk about opportunities for future work, and I'd love to hear your input about them. Lower bounding the quantum complexity and how it evolves under random chaotic type evolutions for an exponentially long time is difficult. People have tried to tackle this problem over many years. They've tried a number of different approaches or used a number of mitigating strategies. People have sometimes focused on just short times instead of exponentially long times, or imagined that we have a global system of high dimensional subsystems rather than qubits. People have leveraged the mathematical toolkit of unitary T designs, which are probability measures that can approximate uniform probability measures. And sometimes people have just assumed that quantum complexity grows as expected, assuming that there are no collisions during an evolution. Here's what I mean by collision, and here's why it's really difficult to lower bound the quantum complexity. Suppose that we're modeling an evolution with a sequence of quantum gates. Later gates can, in principle, cancel earlier gates, lowering the complexity. For instance, suppose that we're running a circuit, we perform this gate, and then we entangle these two qubits with a C0 gate. The complexity probably increases from here to here. However, we might then perform another C0 gate, undoing the gate that we just performed. This is called a collision. The quantum complexity decreases from here to here. We might often assume that collisions basically never happen, and it's reasonable to think that collisions happen very rarely. It's very difficult to prove that they actually don't happen, but of course it's worth trying to prove since we're doing physics and trying to be rigorous about it. Here is the approach that we came up with to prove. We'll focus on a system of n qubits, and for convenience, I'll assume that n is even. We'll imagine these qubits evolving under a circuit, a unitary circuit, consisting of gates in SU4. This is a set of 2-qubit gates. These gates are going to be chosen randomly according to the Haar measure. This is, loosely speaking, the uniformly random measure. It's the unique unitarily invariant measure on the group SU4. Again, these gates don't need to be geometrically local. This random circuit model, although it isn't evolution under a fixed Hamiltonian, which is often a model for chaos, it captures features of chaos. So it's been used a great deal recently to learn about properties of quantum chaos. I will notate the +1 eigenstate of the sigma z operator with 0. And sometimes I will notate tensor products like this. Here's a set of terminology that I'm going to use, and with it, a particular mindset. Let's say that an architecture, denoted by A, is a layout of a fixed number of gates. I'll call that number R. One very common architecture is called a brickwork architecture. In the first layer of gates, a gate acts on qubits 1 and 2, a gate acts on qubits 3 and 4, and so on. In the next layer, a gate acts on qubits 2 and 3, a gate acts on qubits 4 and 5, and so on. And then this coupling pattern repeats itself. If we take an architecture and we choose particular gates to slot into it, then we get a circuit. If we contract the circuit along these lines, then we get a unitary operator on n qubits. So an element of the group SU2 to the n. This contraction is implemented by some map that I'll call FA. It depends on the architecture. Suppose that you take a circuit and you introduce two vertical cuts in it. The gates in between those cuts we'll call a block. A block can contain a backward light cone defined as follows. Suppose that a block has a qubit T that connects to each of the other qubits through paths that go through these gates. For example, this qubit down here enters this gates through which it couples to this qubit, which enters this gates and so couples to this qubit, and so on and so forth until this final qubit links up to this first qubit, which I'm calling T. So there is such a path from this qubit to each of the qubits, and that path might be unique to that other qubit. All of the gates that form all of these paths form the backward light cone. So if a block contains a backward light cone, then in a sense, it's well connected. Does anybody have any questions?
Sorry, I have a very naive question. Why are you looking for a lower bound and not an upper bound? Like, I want to know how fast I can increase the complexity instead of how.
Right. Well, there's a naive bound that's exponentially large that holds for all times. But if we find a lower bound, then we can, well, there's this plot that people often draw that is like what I showed before. It has a ramp here, and then it plateaus. And if there's a lower bound on the complexity, then the complexity might wiggle around a bit above the bound, but we know that at least it has this general form that is expected. And this expected form of the evolution comes from, for instance, the wormhole growth paradox and arguments about entanglement. And so we would like to show that even if there are some wiggles of the actual complexity above the bound, at least there is this lower bound. So at least there is this general shape that's expected. And it's much more difficult to derive a decent lower bound than the upper bound.
Yeah, I mean, as you said, I can have an initial state, all zeros, and then do nothing. Then there won't be any complexity increase.
Right. So the conjecture is specifically about random, chaotic sort of dynamics.
Okay, thank you.
Sure. Any other questions? Okay. We can now state the main result. It concerns an architecture A. This is any architecture that we can form by taking T blocks, each with at most L gates, and concatenating them, putting them together. Each of these blocks must contain a backward light cone. So each of the blocks is somewhat well connected. In an extremely simple example, we can imagine taking a brickwork block with at most L gates for some appropriate number L, and taking T copies of this and concatenating those to form our circuit. Again, R denotes the total number of gates. If we have this architecture, then using it, we can implement many different unitaries by choosing different gates to slot into the architecture. Let U denote any of those unitaries. That is formed by choosing the gates randomly according to the Haar measure. This unitary has an exact circuit complexity, C of U, that is lower bounded by the total number of gates over 9 times the maximum number of gates per block minus the number of qubits over 3. The key part of this bound is the total number of gates R. So there's linear dependence on R. And if we are running a circuit, then as time passes, we perform more and more gates. So the total number of gates is a measure of time. So this lower bound is linear in time as we wanted. Furthermore, this bound holds for a time that's exponentially large in the system size. And that's what we really wanted. There is this term subtracted off, but it's not very important. Again, what's really difficult to prove is a lower bound that's linear that holds for exponentially long times. At times exponential in the system size n, this r is exponential in n, and this term way drowns out this term. So this term is not very important. This is the key part. The key idea behind the proof is a quantity that we call the accessible dimension of an architecture. Here's again an example of an architecture A. We said that if we choose gates to slot into the architecture and then we apply the contraction map, FA, then we get a unitary. The set of all such unitaries that we can implement using this one fixed architecture is the image of this contraction map. And that set of all such unitaries I'll call calligraphic U of A. The accessible dimension of an architecture is intuitively the number of degrees of freedom that we need to describe this set of all unitaries implementable with the architecture locally. To be more precise, I need to introduce some algebraic geometry. So just very basic algebraic geometry. And we're going to use the toolkits of algebraic geometry and differential topology, which are quite different from the toolkits that are very commonly used to characterize quantum complexity, namely Nielsen's differential geometry and unitary T-designs. But the algebraic geometry toolkit gives a different perspective that turned out to be very useful. Suppose that you have a set of equations. It could have a set of solutions. And that set of solution is called an algebraic set. An example algebraic set is SU4 times R. This consists of all the sets of R two-qubit gates. Why does this consist of solutions to a set of equations? Well, a set of equations defines the special unitary group. Each element of the group is in fact a unitary. And because SU4 is the special unitary group, the unitary's determinant has to be positive. Every algebraic set is a semi-algebraic set, which is more general. Suppose that you have a set of equations and inequalities. That set has a set of solutions, which is a semi-algebraic set. The semi-algebraic sets obey the Tarski-Seidenberg principle. Let W denote any semi-algebraic set, and let F denote a polynomial map between real numbers. If you act with the map on the semi-algebraic sets, then you get another semi-algebraic set. In our case, the semi-algebraic set, original semi-algebraic set of interest is SU4 times R, which consists of all the sets of R two-qubit gates. This map, F of interest, is our contraction map, which depends on the architecture. It's a polynomial function because it contracts gates, which are represented by matrices. So this map multiplies matrix elements together in a polynomial manner. And this semi-algebraic set that results from applying our map to the original semi-algebraic set is calligraphic U of A, which is the set of all unitaries that you can implement using this one fixed architecture A. If you have a semi-algebraic set like W prime, then it decomposes into a union of smooth manifolds. One of those manifolds has the greatest dimension out of all of those manifolds. And that greatest dimension is called the dimension of the whole semi-algebraic set. Now, the dimension of the semi-algebraic sets formed from all the unitaries that you can implement using this one architecture A, that dimension is what we call the accessible dimension of the architecture A. Again, this is a measure of the number of degrees of freedom you need to characterize this set of unitaries locally. Does anyone have questions now?
Sorry, Nicole. Sorry. This dimension of W prime. So you contract your matrices, you get a collection of unitaries you have implemented. So this is like a rank thing, or is it the maximum rank, or?
Yes. So in the proof that I'm going to show later, well, actually, so I'll present a proof sketch, and one of the details that I will not show, that was just something that we needed to prove as a lemma, was that the maximum rank of this map is the dimension, the accessible dimension.
I see. So okay, so it's what the okay, good. Thank you. And sorry, so, but you're specializing to this case where you repeat an architecture many times. Is your intuition that?
No. So the architecture just characterizes the whole circuit. So there's the circuit just has some layout of gates, and we're just saying that this whole architecture consists of T blocks. We said that if we introduce two vertical cuts, then the gates in between form a block. So this whole architecture consists of blocks such that each block has a backward light cone. And that actually happens to be a common property. If you just lay out gates randomly, then you will quite probably form a block that has a light cone. So the blocks don't have to be repeated. Just in the really simple example that I keep showing of that involves a brickwork circuit. In that really simple example, you can imagine taking a block that's a brickwork and repeating that to form your circuit. But your circuit doesn't have to consist of repeating blocks.
I see. Thank you.
But sorry, but if you take random things, it's like sort of random walk, so you cannot really prove a strict lower bound. You can only prove a
probabilistic one.
Sorry.
I'm going to talk about that later.
But could you, for example, assume that the angles of the unitary are polynomials in time and try to prove something like that? Or? Sorry,
I didn't hear that.
Because if you prove that the gates are random, you cannot really prove strict lower bounds. You can only prove averages, I guess. But if
the gates are random, then we actually use that. And so our theorem is phrased in terms of random unitary gates, and the theorem is a strict lower bound.
But then I can put all identity, and nothing happens.
No, so the gates are random in the statement of the theorem. They're Haar-random.
Yeah, but you can take a random that gives all ones. Like when you do
random means, as we said in the setup, by random, I mean Haar-random gates.
Yeah, but when you, no, what I mean, if you throw the dice, you can always get one. So you can always get an identity. And
then yes. So we show that that happens with probability 0. And I'll show how that arises in, I think, the next section.
No, but you could have strict lower bounds if you assume something about the gates, for example, that the angles are polynomials in time or things like that.
So we end up proving that if you choose the gates Haar-randomly, then there is a strict lower bound with probability 1, and the anomalous cases that you just discussed happen with probability 0. They form, those types of unitaries form a set of measure 0. So I'll actually explain that in the next section. So we introduced this notion of an architecture's accessible dimension, and it becomes a useful tool in our proof. So we can learn about the accessible dimension using algebraic geometry and differential topology. And from the accessible dimension, we can infer about the complexity, which is what we really want to learn about. Here's a sketch of the proof. First, we lower bound the accessible dimension. This is the hardest step. It turns out that the accessible dimension of our architecture is lower bounded by T, the number of blocks in the circuit. The key elements of the proof include, as I mentioned, algebraic geometry and differential topology. We also construct a particular Clifford circuit. For those unfamiliar with the term, the set of Clifford operators are the operators that transform the Pauli operators to the Pauli operators to within phases. I'll call an n-qubit Pauli string a tensor product of n factors, wherein every factor is a Pauli operator or an identity operator. If you have any non-trivial n-qubit Pauli string, P, then you can always transform it via a Clifford circuit into one particular Pauli string, that which acts non-trivially only on one qubit. We can designate that qubit to be the final qubit, and we can choose for the action of that string to be the Z operator. So you can always construct such a circuit with Clifford operators. Furthermore, the n-qubit Pauli strings form a basis for the space of all n-qubit Hermitian operators. And the number of non-trivial n-qubit Pauli strings is 4 to the n minus 1. Ultimately, that's why our bound holds for exponentially long times for a number of blocks that is like 4 to the n minus 1. After proving, or in addition to proving a lower bound on the accessible dimension, we prove an upper bound on the accessible dimension. The accessible dimension turns out to be upper bounded by 9 times the total number of gates plus 3 times the number of qubits. This proof is simpler, but it still requires some thought. It's based on a parameter counting argument. Feel free to ask about that during the question and answer session. Let's take these lemmata and put them together. Let's recall the theorem's assumptions. We are considering an architecture A formed from T blocks concatenated together. Each block contains a backward light cone and contains at most L gates. The total number of gates R is therefore at most T, the number of blocks, times L, the maximum number of gates per block. If we have this architecture, we can use it to implement many unitaries. The set of all such unitaries is U of A. Suppose that we randomly pluck a unitary from this set, and we ask, what is the probability that we can implement this unitary with a shorter circuit, with fewer gates, with a number R prime of gates less than our bound? Namely, what is the probability that this unitary actually has a circuit complexity that's really small that violates our lower bound? We'll show that the probability of violating the lower bound is 0 by using the 2 lemmata that we just proved, or that I claimed we proved that I had to present because the proofs are pretty long. This is the lesser number of gates that we would imagine trying to use to implement the unitary U. R over L is the total number of gates over the maximum number of gates per block. So we can recast that in terms of T, the total number of blocks. Then we can rearrange the inequality to solve for the number of blocks and find that it's lower bounded by 9 times the lesser number of gates plus 3 times the number of qubits. We've already proved in lemma 1 a lower bound on the accessible dimension, so we can chain these 2 inequalities together to conclude that the accessible dimension of the actual architecture we're interested in is greater than 9 times that lesser number of gates plus 3 times the number of qubits. Now, consider any smaller architecture A prime of this lesser number R prime of gates. We also had an upper bound on the accessible dimension from lemma number 2, and we can apply that to the accessible dimension of this smaller architecture. Then we can chain these 2 inequalities together and conclude that the smaller architecture has an accessible dimension strictly less than the accessible dimension of the larger architecture. That inequality is so important, I'm going to rewrite it. And it implies that the set of all unitaries you can implement with this smaller architecture forms a subset of the set of all unitaries you can implement with a bigger architecture. Furthermore, this set you can implement with a smaller architecture is a subset of measure 0. It's almost non-existent. And to prove this, we use the dimension theory of real algebraic sets. This lemma means that if you randomly pick a U that you can implement with a larger architecture, and you ask, can I also implement it with a smaller architecture? The answer is only with probability 0. So really, for any unitary that you will pick, no, you cannot implement it with a smaller architecture. And that's exactly what we wanted to prove. Now, are there any questions?
I do have a question. So when you say, when you code probabilities here, I'm a little bit confused. So let's say you, what if you can implement a nearby unitary, like some unitary that's close
I'll get to
by?
that soon.
How do you, yeah.
That's a very astute question, and I'll get to that in a few slides.
Okay.
Any further questions?
I do have another question. I got confused about this. I tried to, well, so in your proof, what happens if I just pick, for the sake of I'm trying to understand, what happens if I pick t equal 1? So I don't have, like I don't repeat my blocks.
Mhm.
Everything
Or
goes
you have only one block. Yeah.
Yeah, I just have one block. So the argument holds, it doesn't really matter, right? Is that what the conclusion is?
It should, yes.
Okay. Okay, thank you.
Sure. Therefore, we now have evidence that complexity might be the holographic dual for the volume of a wormhole, or for whatever other quantities grow linearly in time for an exponentially long time in ADS. We can extend this result in a number of ways. First, we can extend the lower bound on the unitary's complexity to a lower bound on the state complexity. Let psi denote any n-qubit pure state. You can define as C sub s the least number of 2-qubit gates that we need to prepare psi from this simple tensor product. We can prepare psi by taking the all 0 state and acting on it with a unitary. If the unitary satisfies the assumptions in our theorem, then the complexity of the state obeys the same lower bound as the unitary complexity, also for an exponentially long time, except this exponential looks a little bit different because the space of states is parameterized differently than the space of unitaries. This extension of our main result proved useful in our resource theory of uncomplexity. You can also imagine making the architecture random. So suppose that we remove from our theorem the assumption that every block in the circuit contains a backward light code. Then we pay by making the lower bound on the circuit complexity probabilistic. In an example of how we could construct a random architecture, we could imagine at each time point randomly picking a pair of nearest neighbor qubits as well as a gate to apply to them. So at this time, we might choose these qubits, then we could choose these qubits, and then these, and so on. With high probability, the gates end up forming backward light cones on their own. If they do, then the unitary complexity obeys a linear lower bound. Here's how the lower bound looks. So this is the probability that the complexity of the unitary that we implement obeys the lower bound. And this lower bound, importantly, as before, depends linearly on R, the total number of gates, which is a proxy for the time. And so what is the probability that the complexity obeys this linear lower bound? It's at least 1 minus some small correction. This is actually a family of bounds because it's parameterized with this parameter alpha. For example, imagine that alpha is large, then this factor here does not suppress this lower bound. So the lower bound we could think of as being quite high. And the associated cost is that this alpha is large, so this denominator is small, so this correction is large, and so the probability that the unitary obeys this really high bound is suppressed. Now, as you might expect from the form of this bound, it was derived using Chebyshev's inequality. Here's what Nima was asking about. What if we want to bound approximate circuit complexity? What do I mean by that? Suppose that we have in mind a unitary U that satisfies the assumptions in our theorem, and we would like to approximate U with a U that you could implement with a shorter circuit, a circuit that violates the bound. We'll call this U prime. If U prime is implementable with a shorter circuit, then with high probability, U prime has a large Frobenius distance from the target unitary. So for all values of some parameter delta, there exists an epsilon such that with a high probability 1 minus delta, the Frobenius distance between the target U and the actually implemented U prime is large, at least epsilon. Unfortunately, this epsilon can be uncontrollably small, so that this result isn't the most interesting. Because if epsilon is really, really, really close to 0, then this basically just means that U, the target unitary, and the approximation are at least a distance 0 apart, which isn't terribly profound. Why is this result of this form? Why can't we control how small epsilon is? Well, we're imagining taking this set of approximation architectures, so we're imagining having this target unitary U, and we want to approximate it with a U prime implemented with some shorter architecture A prime. Now consider the set of unitaries that we can implement with U prime. We're saying, suppose that we implement one of these U primes, then it's as though we were implementing a unitary in a larger set. Because if we implement any of these approximations U prime, then it's as though we were implementing any target unitary that's epsilon close. And so we're taking this set of unitaries U prime and growing it in all directions in the space of unitaries. And if we grow this set in all directions, then we increase its accessible dimension to its maximum possible value. And so that really, really important inequality that I presented in the proof is generally not satisfied. This suggests that the accessible dimension, while really useful for solving the really hard problem of how does the exact quantum circuit complexity grow, is a bit too crude to prove the desired results about approximate circuit complexity. But that just leads to an opportunity for future work, which is to strongly lower bound the approximate circuit complexity. So we might, it could be still useful to think about this set of all unitaries U implementable with the actual architecture A that we have in mind, and the set U of A prime that consists of the approximations. But we might need to think about not just these two sets accessible dimensions, but the way in which they overlap in the space of all unitaries. If we can strongly lower bound the approximate circuit complexity, then we can lower bound Nielsen's complexity, which high energy theorists would like to do. Nielsen's complexity is known to upper bound the approximate circuit complexity, and if we can lower bound that with 1, then we have lower bounded Nielsen's complexity. Also, this work introduces this concept of the accessible dimension as a new tool, a mathematical tool in many-body quantum physics. Again, it's very different from the toolkits that are usually used in the domain of quantum complexity, Nielsen's differential geometry and unitary T designs, but it turned out to be really useful for proving this result about a lower bound on the exact circuit complexity that had been sought for a while. So since it was useful in this problem, we hope that it could be useful in other problems in the future that involve some random type evolution. And I'd be interested in hearing if anyone thinks that there might be opportunities to use it in holography. And by the way, my co-author Jonas deserves all the credit for coming up with this idea of the accessible dimension. So I didn't talk a whole lot about the resource theory for uncomplexity, but there are more opportunities that are related to it that you can find in this paper. In summary, we said that quantum complexity is a relevant concept that's been appearing across subfields of quantum many-body physics. Adam and Lenny formalized two conjectures about complexity in this much used paper. First, they conjectured that the complexity of a system evolving under a random chaotic evolution tends to grow linearly in time for an exponentially long time. Second, they conjectured that one can define a resource theory for quantum uncomplexity. I presented the outline of one of the proofs and also mentioned that this resource theory has now been defined. We use the toolkits of algebraic geometry and differential topology, especially using this notion of the accessible dimension of an architecture of a class of circuits. And there's much to be done. So thanks for your time.
Thank you so much for the beautiful talk, Nicole. Are there questions? I actually have a question. I got a little bit confused about the approximate statement. So the statement that you show at the end is, so you show that if I want, if I say that I want to say come close to the unitary up to some epsilon in Frobenius norm, then you do not have a lower bound, or I got a little bit confused, sorry.
Yeah, I'll go back to the relevant slide and then share my screen again. Here we go.
Okay, so
Suppose that we want to implement the unitary U, but what we actually implement is some other unitary U prime that's implemented by any circuit that violates our bound. So it's a particularly small circuit, or smaller than you might expect you need. Then U prime and U are somewhat far apart. The Frobenius distance between them obeys this lower bound.
there exists an epsilon of A and epsilon. So the conclusion is that they are probably far apart, right?
Yes.
That's what the conclusion is. So that's what we expect from physics. I see. Thank you.
Sure.
Any other questions? I do have another quick question. You mentioned at the very beginning, this might be a little bit off topic. You mentioned in the beginning that people have tried using T designs and to relate to these complexity type bounds. In your work, T designs don't come up, or do they?
They don't. This is a totally different mathematical toolkit.
Yeah, so is there, okay, all right, thank you.
Sure.
Any other questions? If not, let's thank Nicole again.
Thanks for having me over.
Thank you so much. And I'll share with you the link when we put it on YouTube. Thank you so
Great,
much.
thank you.
Have a great day.
You too.